Recording's rolling. It's Tuesday, October 28th. Yesterday we started on an entirely brand new topic, a completely new way of thinking about things. Got new variables, new units, joules, watts, so I'm going to pick up about where I left off yesterday. I'll give you guys a quick recap and then I'll pick up there. Yesterday I did give you guys this three-page table. We never quite got to this. It has 12 different scenarios on it. Most of them are closed systems. These two are open. So we get to those. So we're working our way towards that. We might get to some of this day. All right. AP classes. AP Classroom Unit 3 is open. Guys, when are you guys going to finish this by? Monday. Yeah, before you come to school on Monday, so that we can go over the answers by then. I think by the end of this week, you should be able to answer all the questions. We'll cover everything. All right. So, any questions about what we're doing? Okay, so let's do. Oh yeah, what's that? So like a handout or yeah, just this right here. Did you get this yet? Okay. All right. All right. So, here, quick recap of yesterday. We've got this entirely new concept. We're talking about energy, which is measured in, guys. What does J stand for? Joules. Right. And joules breaks down into, Newton's times meters, which further breaks down to kilogram meters per second squared. And the funny thing about this unit right here, joules, is that there's exactly the same number of joules in the universe today as there were 10 billion years ago. There will be 10 billion years from now. You cannot create or destroy energy units. All right, so that's good. Now, what you can do is you can transfer different forms. So work is a transfer of energy. But careful, guys. This capital W is a variable, stands for work. Okay. But later on, way down here, this capital W as a unit stands for what? Watts. Or should say stands for watt. And then that is a rate of energy transfer, like joules per second. Hey, if you're ever plugging like a 20-watt light bulb that's drawing 20 joules per second, if that's what watt. All right, so careful about that. You can have energy of location, like if I pick up something, put it on a shelf, call it gravitational potential energy. You can have energy stored in a spring. I'll call that spring potential energy, which is different than a force. Right now, it takes a force to construct a spring, but it also takes some energy. That's a different concept. This would do different kinds of equations with that. Energy motion is called kinetic energy. And there's also a rotational form of kinetic energy, like a ball rolling across the floor, or maybe this rolling across. But we're not going to worry about that one for a few months. Okay, and don't worry about momentum yet. That's not for a couple weeks. Right, so, okay, show you guys these units. These are your building blocks. So when we're putting in conservation of energy equations together, which we did start to do yesterday, pretty much you just draw from this list. This is pretty much the list you care about. Okay? So these are forms of mechanical energy. So work is a transfer of energy, force and distance. It's a dot product, so it has to be all in the same direction. So you can lift something some height, if you lift something diagonally up some stairs, it's really the height change that matters, not the horizontal type of motion. It doesn't take any energy to transfer horizontal. Okay? If you're pushing a shopping cart, and you're moving it forwards, and you have a forward fork, there's a resistive friction force pushing you guys back. Right? The work you do it's really just all in the forward direction. So if you're pushing down forward, it's only forward. Right? That's what all goes in this dot product. Now, if you lift something a certain height, well, actually, this leads to this because I have to lift with the force equal to its weight mg, and the distance I lifted is height. Right? So if I lift this and put it on a shelf, clunk, or I lift this, put it on a shelf, clunk. It takes some work to do that, and that's transferred to this height. Now, let's see if I can get this one by the end of today. What if you have a changing gravity field? What if you send a rocket all the way from Earth to the moon? This gravity field would not be constant at all. Right? So you can't really use MGH at that point. MGH is really nice if you're kind of stuck on the surface of the planet, but otherwise it kind of falls apart. So there's a more universal form. And I do have a poster to show you that this does simplify to this. So see if we can say you need this to have to derive escape speed from a planet, or to if you have in the middle of deep space like two asteroids, right, so the gravity field's always changing. Right, how much energy is stored in a spring? I showed you guys no Hooke's law. You guys know F equals kx, but the area under that represent looks like a triangle shape. You guys see that later. Energy stored in a spring. How much energy does it take to stretch this amount? 1/2 kx squared. And energy motion ends up being 1/2 mv squared. Okay. And we're not going to worry about rotation for a few months, but you see these are kind of analogous, right? Okay. So we got that. So we got work force and systems dot product. Ooh, guys, you're gonna see a bunch of these type graphs all over the exam. If you ever see force versus distance, okay, once you identify those axes, almost for certain the question's gonna be something about work or energy transfer. And what property of force versus distance tells you how much work has been done? The area under the curve. Okay. Now here I'm showing a constant force. Could you have a variable force? Could you have like a changing force? Yeah. In fact, classic example is Hooke's law. Okay. The more force I apply, the more the string stretches. Right. So that's like a variable force. Now it's still a force versus distance graph. So the area in the curve still represents some kind of work or energy stored. Okay. And in terms of like the spring, and so we want to have k squared. K is how stiff is the spring constant. X is how much you stretch it. Or it could be compressed. Right. Right, kinetic energy. Well, I want to make this poster, but that's not too much. Right. 1/2 mv squared. That's all you have to know. Kinetic energy is 1/2 mv squared. Say the mass of a car, speed of a car, put it all together. Okay. All right. Ooh, this one looks simple, but this is really critically important poster here. Okay. So if you have a closed system, sum of energy initial equals sum of energy final. This says conservation of energy. Energy is conserved. You cannot create or destroy energy. Okay. Now, if you have what's called an open system, then there might be work done on or by the system, hence the plus or minus the work. So you have joules plus or minus joules equals some final joules. Okay. My classic example for this one is a car brakes to a stop. So when you see that, okay. No, this terminology like closed or open. AP uses this terminology for exactly this. Some textbooks, especially if you get to thermodynamics, might call this more like an isolated system. So if you get to like a higher level college class, and they say, well, actually, an isolated system is different from a closed system. Okay, it depends whether you allow energy in or mass in or something. I'm just gonna call it. I'm just stick to AP terminology here. All right, and then here's our main first classic example of conservation of energy. Because this one's real classic. Galileo drops the ball. How fast is the ball crashing on the ground? Which you could have answered months ago. Guys, could you have broken out this third kinematic formula? Said, oh, here's the height of the building, here's gravity field, here's the crash speed, boom, boom. Okay. But now we have a new way of thinking about it. Because what type of energy at the top? Potential energy. So you write down MGH. What type of energy at the bottom? Kinetic. Yeah, or 1/2 mv squared, same thing. Yeah. And is this quantity here equal to this quantity here? If this is 1,000 joules, is this 1,000 joules? Yeah. So you say energy is conserved, so you set those equal to each other. Okay. And then you can solve for whatever you want. In this case, maybe the speed. Okay. The mass of the ball cancels out. Hey, no surprise there, shouldn't be. Okay. We got this is very similar idea. What if you throw a ball upwards? Right? How high can you go based on your throwing speed, or what is your throwing speed based on how high it goes? Okay. Here's the old way of doing it. Here's the new way of doing it. Okay. Pretty similar to the Galileo question. Right? Car rolls uphill. What type of energy at the bottom? It's all kinetic, all motion energy, which is somehow 1/2 mv squared, and the VM column, V bottom. Here, guys, listen. No, let's say you let the car just coast to the top, so you're not slamming on the gas pedal, nothing like that. And we're ignoring frictional losses. Is the car going slower at the top? Yeah, even if there's no frictional losses, just the fact that it had to find this height, some of the energy would be diverted into like lifting it against the gravity field. Okay? That's called MGH. And whatever you have left over goes into its final motion 1/2 mv squared. Right? So maybe this is like 1,000 joules, and maybe this is like 300 joules and 700 joules, or whatever the numbers turn out to be. You guys get the idea, right? And if you know most of these variables, you can solve for whatever you want to solve for. I like this one because it involves three sort of forms of energy. Okay? So you press this block against the spring, let go, flies around the loop. Okay? And notice with all these conservation setups, I'm always going from some point A to some point B, initial to final. Maybe my final point, I take the top of the loop. I want to know something that can make it around or something like that. Okay? So I want to know how fast is it going to the top. Okay? Well, guys, what type of energy did it start out with? Yeah, spring potential, right? 1 k squared, right? And then by the time it gets to here, well, I think the energy kind of went into sort of two forms. What and also what? Yeah, gravitational potential, MGH, had to be lifted this height. And to count in terms of energy, the term for that is called MGH. Yeah, and also it has some kind of speed. Right? So what's the energy of motion? 1/2 mv squared. Okay, so you guys see? Right? And in your notes yesterday, I made up some numbers on the fly and we solved for what the speed be. If I give you the mass and the gravity field and this height change, the spring constant, and how much you compress the spring start with, okay, there's enough information you can solve for how fast it's going at the top. You guys see that? Okay. Threw in some numbers yesterday. Okay. This one I stole off an old APFRQ. Right? Some do with like a bungee jump. Can you treat a bungee cord basically as a spring? Right? So he starts off with gravitational potential energy here, MGH. Now this H is kind of a special H. I just added together this L plus X. Okay. And then by the time he's suppose he just the stretch is just so he can reach out, boop, just touch the sidewalk below, and then before it retracts. Right? Well, in that case, he wouldn't have any motion anymore, so he has no kinetic. He also has no height. We're defining height 0 down here. Right? So where did all the energy go? It went into the bungee cord, which we're treating as a spring, so 1/kx². Right? Well, this x is how much stretch. Right? So if this is 1,000 joules, this is 1,000 joules. All right. Ooh, played a video for you guys yesterday on this one. All right, now this one's a little involved, a little complex, but this is a really classic question. Right, what's the minimum height of a roller coaster hill to make sure you get around this vertical loop? Something like that. Now you have to go back to a week or two ago to say, well, there is a minimum speed to get around here. So that's like the water in the cup question from a week or two ago. Right? And then conservation of energy. Because how high does this hill have to be? Well, it's all potential energy at the top. So I write down MGH. That's like the source of energy. Okay? Then by the time it gets to the top of the loop here, well, it does have a height, and the height is 2r, isn't it? It has some potential energy. If I'm defining the floor is way down here, it's height 0, right? Okay. And it better have some speed and some kinetic energy, 1/2mv². But how much speed? Well, that goes back to a week or two ago. So you do substitution, then a bunch of algebra. And the answer is always this, right? This, again, classic physics question. So notice that the mass of the cart cancels out. The gravity field also cancels out. So if you took this whole system to the moon, the answer would be exactly the same. Ooh, I think this is the last one you guys saw yesterday. You guys remember this? And then the bell was ringing. Right. No, this one I do want to have you guys do a lab on. So I'll give you guys this lab table sometime in the next week or so, where you hook on some weights or some lab assets. You let it swing. I'm gonna give you guys a motion detector, like a little speed gate. Yeah, so you get an empirical measurement of what's that speed at the bottom. But I also want you to calculate what should the ideal speed be according to this right here. In the past, this has worked out really well. So these last columns always match. Okay. So if this starts from rest, this starts with what kind of energy right here? Potential energy. So I write down MGH. Okay. Now, as long as I start from rest, that's all there is to it. More is graded. Right, we'll come back to that later. Okay. And then at the bottom, it's all what kind of energy? Kinetic. So 1/2mv², which does not look just like the Galileo question starting out. MGH is 1/2mv². That's not too bad, right? Right? In fact, if you just drop this straight down, would the speed just be square root 2gh, wouldn't it? Right? And actually, that's all this is too. It's just speed is square root 2gh, right? You see that? Square root 2, square root, I got 2g, and then, well, something to do with height, right? Now, the fun trick about this one is the extra geometry to figure out what is this height change based on this length and this angle, right? You guys see that? Right? So, if this angle was like 2 degrees, there'd be very tiny height change, almost nothing. Okay. Guys, what if this angle was 90 degrees? Ooh. Would this height difference be equal to the length of the string? Yeah, that would be true, right? What if this angle's like 36 degrees or just whatever crazy number? Now what? Okay. So let's go through the geometry. Okay. So do you guys see a right triangle right there?
Yeah.
Guys, what is this side of the right triangle equal to in terms of L and theta? L cosine theta. Yeah, exactly. L cosine theta. And is this length string equal to this length string right here? Yeah. So length of string is still L, right? So if this is L cosine theta, then what is this height change equal to?
The L minus.
Yeah, exactly. L minus L cosine theta. Yeah, that's all. Sorry, right? Okay. And then it's common to factor out an L. You don't have to, but you could. Right? That's why it looks like this. L times 1 is cosine theta. You see that? Right. So be able to do that. I'm just showing you guys how to do it, but you should be able to do this. Right? Better if you're taking notes and so you can build that muscle memory. Another detail here is what if you don't really sit from rest? What if you give it a little push? Then it does start out with some kinetic energy, doesn't it? Okay. Same thing with if I go back to let me dig through find out Galileo here. Here's Galileo. Okay. What if Galileo didn't drop the ball? What if he threw the ball straight down? Okay. Actually, here maybe we'll go back to that. Let's go back to Galileo. Okay. So what if Galileo doesn't drop the ball? What if he throws the ball? Let me give you guys some multiple choice answers for what is the crash speed. Are you guys ready for that? What is the crash speed?
Yeah.
Okay. So I give you guys two options, A and B. Is the crash speed equal to, and one of these was right and one of these was wrong, which one's which? Okay. Is it equal to his throwing speed plus the square root 2gh? Because if he drops it, this crash speed is just square root 2gh, right? Okay. So what if he throws it? Is it that? Or is it the square root of the throwing speed squared plus 2gh? Okay. Show of hands. How many of you guys think it's option A? Is option A correct? Who says option B? Oh, yeah, yeah, we did this yesterday. Yeah. Bing. Oh, look at all my winners out there. Yeah, I think everybody got that. Yes, got that. It is that. Right. Now, you could show that through kinematic motion. Actually, you know what? It's right here, isn't it? You just take square root of both sides, and it's exactly what you guys said. You just throw a big old square root of this whole thing. Okay. Um, or the new way of doing it is conservation of energy. So if you include the initial kinetic energy term, right, now mass of the ball ends up canceling mass of the wait, right? But it does go up as square root of the push speed squared plus 2gh. Okay. You guys remember that? All right. Shuffle all this over. All right, so I think we're moving on to new territory here. Actually, I think it's time for a good video demo break. All right, so I got a special one for you guys today. Let's see. Energy. I got. Where'd he go? Ah, here he is. Mark Rober. No, this is a video from a few years back. He's showing Pinewood Derby car. He's saying, like, what's the science of constructing the best Pinewood Derby car? Do you guys know this concept? It's like, where's this ramp? Give you guys a bit. Yeah, you guys see that incline there? Okay, so you start with a couple cars side by side, the top of that incline. You release them, they zoom, and whoever car cross through the finish line first, right? Right, so it goes fastest. And he has some science here, like empirical science, so that he backs up. But a lot of this explanation has to do with conservation of energy, like straight conservation of energy. Right, so see if I can find a couple of tips for you guys to how build the best car. Right, so where was it here? Looking for right here, right here. Right. So one of the big tips was where to locate the center mass. Should you locate it kind of towards the front of the car or the back of the car? It makes a difference. Do you guys see that the if you put the center mass near the front of the car, this blue car is basically done accelerating and it's just going to coast from here on out. But the red car is still sort of falling, isn't it? Do you guys see that? Right. So it's getting sort of a boost, right? Sort of a boost, right? And that's like back at the beginning, the red car would have had more potential energy at the beginning, hence it has more kinetic energy at the end. Right? Hence it'll be more likely to win the race. Right. Um, right. And then all right, he does a bunch of tips. You guys see his blocks right here? Right. He's saying all that blue represents potential energy, so he's quantifying it sort of like blocks. Right. Maybe this green is translational kinetic, how fast the car going. Maybe this red is like friction, so you can subtract out a little bit. Right. That's a little bit of an open system, so hold on to that idea. You'll see that later. Right. But he's saying, hey, some energy actually does go into making the wheels rotate. Don't forget about that too. So he's representing that with these yellow blocks. So it's a different form of kinetics, like a rotational kinetic. You guys see that? Right? He says, you know what, guys? What if that car has four wheels on it, right? Right? What if you bent one of the axles so that the car was really only resting on three wheels, hence only three wheels were rotating, one's just kind of just hanging out, right? Wouldn't that wouldn't some of the energy that was being diverted to making all four wheels rotate instead go towards making the car just go forward, right? Because you start off with the same potential energy regardless. The car starts off at the top of the incline with all these blue blocks, right? All these blue blocks here have to equate to all these other blocks by the time it gets to the end. Someone to friction, that's just loss. That's these red blocks here. Right? Someone to translational kinetic, making this car go. That's really what you want. You want to try to maximize translational kinetic, these green blocks. Right? But rotational kinetic, the wheels rotating, that all right. All right. What if I can just make three wheels rotate? So that's what he does, I think, somewhere in here. He says, we're going to build one of these wheels. Okay, it's going through a bunch of explanation. Yeah, lift one wheel, lift one wheel. Okay, if you lift one wheel, you'll win by 1.1 car lengths, okay? And there's a bunch of other factors goes through. Okay, yeah, you guys see he's taken one of those four yellow blocks, and it's one of the four wheels. He's turning it into a green block, which represents now translational kinetic energy. Now the car is going faster, it's going to win the race. You guys see that? Right. All right, so there's a whole video here. I just wanted to point out a couple of points. Right. All right, so you guys go with the Pinewood Derby car. How to win that race. Okay. Yeah, it's all big in terms of conservation of energy. All right. Now this next one's a big one. Okay, you guys ready to go back to posters? This one's a big one. This is actually also one of your examples on the three-page table we're going to go through. Car brakes to a stop. Now, what if I want to know what is this braking distance as a function of the initial speed of the car? Now, you have to know some other things like the coefficient of friction. Because guys, if there's no friction in the road, the car would never stop, would it? Right? Or what if the road is iced over, or if a wet road versus a dry road, those would all be different outcomes. So the coefficient of friction definitely matters, right? Okay, but if you were given the coefficient of friction, what is the relationship between the initial speed and the stopping distance, right? And a proportionate question I like to ask is, what if you triple your initial speed? What if you're going like 20 miles an hour and you brake to stop? And you can just triple that to 60 miles an hour and brake to stop. Guys, triple the speed. Guess what's going to happen to the distance? Well, let's find. Yeah, it's definitely going to increase. But I wonder if it's also going to triple, or if it's going to be square root of 3 as far, or it's going to be 9 times as far. Well, what was going to be? Okay. Now, do you think you could solve this by going back to maybe a combination of kinematic motion and Newton's second law of motion, and you can put it together, and you could totally solve it already. Based on what you know from even from last week, or up to last week. But there's a more efficient way to solve this exact question, and that's to set up an open system and go through energy expression. So, guys, what type of energy does this car have right before he hits the brakes? Kinetic. And what's the formula for kinetic? 1/2 mv squared. Yeah. Okay. Now this symmetry is what's called an open system. So when the car is braking to a stop, is all the energy being transferred into friction or work done by friction between the tires and the road? Right. You guys, what's the formula for work?
Force times distance.
Force times distance, exactly. Right. Now in this case, it's a forward distance, but it's a backward acting force, isn't it? Isn't it friction pushing against? Actually, I'm showing it right here. Here it is. Here's the car's moving forward, but it's a backward acting friction. That's why I'm subtracting it off. And AP might phrase it like friction is doing negative work on the car. Okay? Just like that. Because by the time car comes to a stop, how much mechanical energy does it have at that point? Well, let's go through the types. Does it have any kinetic at that point? No, because it has no motion. Does it have any gravitational potential? Did it go up any hills to come to a stop? No. Although that could have helped if it went up a hill, could have stopped it faster. Right? It doesn't have any of that. So there's no gravitational potential. There's no springs. Right? So how much mechanical energy does it have? Zero. Yeah. Right. Wait a minute. Did the energy just disappear from the universe? It started off with a bunch over here. Or do you think if you took a thermometer and you measured the temperature of the road, what do you think happens to the temperature of the road? It goes up a little bit, right? Now, that's not one of our mechanical forms. Here, I'll show you guys. Okay. That's not actually on this list. I would write as MC delta T. That's not here. So all you care about is that it just dissipates from friction, maybe heats up the road. Right? But we're going to focus on the mechanical parts. Right? So this is exactly what you guys just told me, because I just asked you. You said, oh, well, it starts off with kinetic. That's 1/2 mv squared. Okay? The energy is dissipated by friction, so that's force times distance. We're subtracting that off. Right? And it ends up with 0 at the end. And that would be joules, 0 joules. Right? You guys get that? Okay. Right. Now, the next step, and I see some of you guys take notes, which is awesome because that'll help you learn this even better if you write this down. Right? What is the relationship between this initial speed and this distance? Isn't that how I just framed that? I said, what if you triple your initial speed? What happens to the braking distance? Right? And I think I can slip some more steps in here. It looks like I did put in one more line in the screen box. All right, so let's see what else could we come up with. How about this friction force? Guys, is this friction force related to this normal force? Yeah. Guys, friction force is normal force times what? Exactly, coefficient of friction. So do you think I should probably substitute for this friction force? The coefficient of friction times normal force? Okay. But you guys have done this several times in the past, where as long as you have a flat road, which we do, a level road, what is this normal force also equal to? The weight of the car. You guys see that this is going to match this? As long as you have a level road. Okay. It changes on an inclined road, but you don't see that too often. Okay. You guys see that? Okay. So that's exactly the next substitution. Actually, it's a double substitution. I sort of skipped this step going from here to here. Okay. But the 1/2 mv squared, that stays the same. Okay. This friction force turns out after a couple steps to be, coefficient of friction times the weight of the car, because that's equivalent to a normal force. Okay. And then you have the braking distance. Okay. So the car starts off with some number of joules of kinetic energy. All those joules are dissipated into friction force and heat up the road, and so the car ends up with no mechanical energy at the end. Right, you guys see that whole process? Right. Now, maybe I want to solve for the stopping distance. Guys, go ahead and do that right now. Right? I see some of you guys are definitely taking notes, which is awesome. Right. So do some algebra. Right? And everybody has paper in front of them. Give everybody paper. Okay. I want everybody to solve for this braking distance right here. Here, I'll point to it with an ink pen. Solve for that braking distance right there in terms of everything else. Everybody's solving for D right now. I'm taking a trip around the room. See if you can solve for that braking distance D. Okay. You can solve for braking distance. Everybody's solving for the braking distance. Solving for the braking distance. All right. Give you guys a hint. I think some of you guys figured this out. Is there a variable that's gonna sort of cancel out? Yeah. You guys have that? The mass of the car, right? What wasn't that true in the past? I've asked a similar question in the past. If you have you guys remember there's a empty car versus a car full of groceries, and they have the same tires on the same road and so on. Right? And they end up braking the same distance, all else equal, if they start at the same speed and so on. Right? Yeah, the mass of the car ends up canceling out. Okay. So you do need soul mass to make this happen, but once you have soul mass, it doesn't matter how much mass. Okay. So I think I could, let's see, add one of these terms over. Yeah, mass cancels out. Okay. And then if I want to solve for D, to basically just divide by the mu and the G. Right? So take this, divide by the mu and the G. And this 2, I guess, could also show up in the denominator also, right? Right? Put it all together. Did you guys get exactly this expression right here? This right here? Right? Because if you did, you are winning. Got lots of winners out there. Right? Get exactly this. Right? So this last line just turns into this right here. Solve for D. Okay, get that? Right. Right. Now to that question, like, well, what if you go back and you triple the speed of the car? What happens to the braking distance? And you see right here, and I pulled out this relationship because this is such a classic question. If you triple the initial speed of the car, what happens to the braking distance? All else equal. I just pull this out as proportionality. And guys, what's the answer to that question? 9 times the distance. You guys see 3 times the speed is going to result in 9 times the distance because 3 squared, right? If you want to make up a whole bunch of numbers and plug them all in, it doesn't matter what numbers you make up, you'll always get that proportional relationship. Okay. You guys go with car braking to a stop. Because that will definitely not be the last time you see this. So know this one. That's a good one to know. Right. So that's my classic open system. Right. Let's go back to closed systems. You guys ready to go back to closed systems? Right. So there's my open system with just the car. Right. Closed system. Hey, it's Atwoods. They're back. Now, you guys remember doing the lab with the Atwoods? I gave you guys these pulleys and little lab weights and the string, and you rig these up. You guys remember that? Okay. Back in the day, a few weeks ago, I was asking you guys, what's the acceleration of the system based on the 2 masses? Right? That was the main target question. And then, once you know the acceleration from Newton's second law, right, could you kick back over to kinematic and figure out anything else I wonder how far it's gone after so much time, or how fast after so much time, or how fast after some distance moved. You can answer all those questions once you know the acceleration. Can you do that? Right. Now we have a new way of thinking about the question. And you can solve this all with energy. Right? Actually, let me just sort of backwards. Is what question would you even be asked? Guys, if you're ever framing something with energy, can you ever answer something after how much time has passed? No, because time is not showing up in these energy equations. Okay, so maybe kind of a limitation, right? But guys, it seems like I'm trying and pulling this third kinematic equation over and over and relating it to what we're doing here with energy, right? Because this one doesn't involve time. Doesn't this last one answer how fast as a function of distance moved, right? And that actually is like a prime energy opportunity, right? And that would be the question. It's like after some distance move, which I've labeled h, like a height change, how fast is it moving? That's what you could answer really quickly with the conservation of energy setup. Is that right? And notice with the setup, you don't actually even have to solve for the acceleration to get there. You could go over to kinematics. That's just a different way to do it. Right? Here's your setup. So cover this up here. Okay. So I'm going to identify a mass 1, mass 2 Earth system. So I am bringing in Earth to make this a closed system. If you could ask that could be their question. They say, what's in the closed system? You say, okay, I got each of the masses and also the Earth. Don't forget the Earth, because if you leave the Earth out, now these would be external forces. Okay? But if I bring in the Earth, now I've internalized the Earth into the system. I've internalized these forces. Okay. Okay. So I got the conservation of energy here. Sum of energy initial equals sum of energy final. Okay. All right, now what? And it's there's a few different ways to kind of set this up, but at least the same outcome. Right. Guys, isn't the heavy block going to fall down and that's going to lift the small block? Isn't that exactly what's going to happen? Okay. And while it's happening, if this is a continuous process, if you arbitrarily cut off some height change, aren't the blocks in motion at the end of that height change? They don't come to a stop; they are in motion, right? So let's put it all together, right? So the fact that the large block is falling, isn't that sort of like the supply of energy? Is that okay? Does everybody get that? Like the large block falling is the supply of energy. So when I say the supply of energy, what term do I write right here? Potential energy, mgh. Right. And so which M? M1 or M2?
M2.
M2, because it looks like M2 is bigger, right? Right. So does it have to be M2GH? Is that good? Let me make sure I wrote that. I did write that. Yeah. That is M2GH. That's like the source of the energy, right? Right. Now that source of energy ends up doing three different things. That's what's one thing that this large flying block does. It does what? Yeah, it will get transferred to kinetic, right? Actually, you know what? Is it for both blocks? Do both blocks have kinetic? Yeah, they sure do. Now, one's moving up, one's moving down. Does the direction matter? Does it matter that one's going up, one's going down? Not in this case. Yeah, not in this case, right? Maybe in the past you have to consider like up versus down. But energy's a scalar. You guys remember energy's a scalar? Right. So that's two of my energies. Actually, the next one I got is the third thing that happens. Right? Because what else does the falling block do? It also does what to the small block? It lifts it, doesn't it? Okay. Which gives it what kind of energy? Gravitational potential. Yeah. Right. So I'm going to write lifts the small block in 1gh. That's like sort of one of the demands for energy. Right. So if the large block falling, suppose it like loses 100 joules, could it maybe give the small block like 30 joules in lifting it? Right. And then maybe you have 70 joules left over, and some of those go into the motion of one block and some go into the motion of the other. Okay. Now, since this is a conservation of energy, remember, like all these setups, you're just choosing from like this equation bank right here. Here's your equation bank. All I'm doing is I'm just pulling off this list, and it's just a real short list, isn't it? Mechanical energy forms, right? That's exactly what we're looking at, right? So the large block falling lifts the small block. And also at the end of this arbitrary distance, each block has some speed. They're in motion. So I have some kinetic energy also. Right? Right, just like that. Can you guys come up with that? Right. All right. And then what if I threw some numbers at you? What if I told you the masses of these blocks? I told you the gravity field. I told you, let's say we have a height change of so many meters. Right? Do you think you could solve for this V if you knew enough? Right. Now this V does show up in two different places, two different terms. So maybe you have to like subtract this term over and then divide. Okay, I have to maybe factor out the v squared. You can do that. You can solve for v, right? You guys can do that. Okay. All right. How about do you guys want to do a numerical example? Yeah. Okay. Let's do it. Okay. So let's do exactly this. What if I give you mass 2, mass 1? Let's call them. How about 5 kilograms and 4 kilograms? Okay. Let's go. Gravity field is 10 meters per second squared. Let's say that arbitrary height change is like 40 centimeters. That could look realistic, right? Maybe something kind of like that. Yeah. Right. Can you solve for the speed at the end of the motion? Right. So can I fit this all on one screen? Yeah, that fits right there. Okay. So I'll solve it. You guys solve it. Right. I'll solve it off screen. You guys solve it off screen. Okay. Maybe I'll do it on paper so I can show you what I've been doing. Meantime. Okay. All right, let's see what we come up with. All right, see if you guys can beat me to the answer. Yeah. Okay, I'm gonna pause this video. Let's watch this video at home. Let's hit pause. All right, here. I'm gonna unpause the video. I just unpause it just to throw you guys a hint. How many guys caught that? Okay, guys, can you feed all these numbers straight into a calculator? Which one do you have to change a little bit?
Right.
Yeah. This height change. Do you guys catch that? Right. I just want to make sure you're not getting too far off track. Guys, what number should actually go into the calculator for the height? 0.4, because that's how many meters, right? For base SI units. All right. Here, go back and pause this video and let you guys finish that. All right, we're back recording. So just walk around the room. Yeah, a bunch of you guys actually did get it. I think about 5 or 6 guys got it, which is awesome. So show you guys exactly what I did. So here's my conservation of energy setup. So the large block falling lifts the small block and gives each block a speed or kinetic energy, you can say, at the end of the motion. I plugged in all these numbers. Okay. And turned out, did you guys get there's 20 joules to go around? 20 joules. Okay. Now 16 of those joules went to lifting the small block, which means I guess you have 4 joules left over, don't you? So 20 minus 16 is 4. Okay. Now you have something v squared plus something v squared. Different ways to do this. You could factor the v squared out, or you could tag these together. Probably did. Last algebra steps. Divide over this number of kilograms, it turns out, and then take the square root. And I got 0.94 meters per second. Okay. That should be the answer with these input numbers. All right, so there you go. Pretty good. Pretty good. Yeah.
Don't you got like 0.8?
Well, okay, yeah. 0.89 was v squared. So 8 over 9, 0.89 was v squared. So the last step is to take the square root. Yeah. Okay. Okay. Yeah, so the last step was square root. All right. Here's a little bit different setup. You guys remember this modify that way? Right, maybe this one's on wheels, you get rid of the friction. Right. So this one, this one block is falling. Right, you guys remember that, right? That's the same system as before. I got M1 and 2 Earth system. Let's do conservation of energy, which again could really efficiently answer the question, how fast is it moving after some height change? Notice they labeled a height change here. Okay? So guys, what's the sort of source of energy for initial energy? What should I put? Yeah, potential energy, MGH. You see the fact that this block is going to fall, it's sort of like providing the energy for the system. Okay. So M1GH, it should be. Yeah, there it is, M1GH. Is that true? Okay. Now, at the end of this falling motion, it hasn't hit the floor yet. Right? Once it says that changes everything. Right? Hasn't hit the floor. Is it in motion? Is this top block also in motion? Okay. But notice this top block didn't actually change height. It just was given that kinetic energy, wasn't it? So how should this finish off? Each of these blocks has a 1/2 mv squared. Yeah. Right. If I define the lowest point as height 0, that would be true. Right. Like it's like 1 millimeter above the floor, so it's in motion, but it hasn't crashed yet. You can set up that right there. I mean, that's pretty straightforward setup. How about what if there was friction on the top block? Ooh, this one's got some friction going on. Right? And let's make it more complicated. So put it all together. Guys, what if this block on the right is falling down and it's causing this block on the left to be lifted? Of course, it's the same height, right? Just one's going down, one's going up. Right? And this top block also has some friction with the surface. So now I have an open system, don't I? I have to subtract off this work done by friction. So the large block falling, that's my MGH falling, that's supplying the energy. I do have to subtract off this work done by friction. Kind of reminds me of that car braking to a stop, doesn't it? Sort of thing. Okay. And whatever's left over actually goes into 4 places. 4 places. Woo! You have to lift the small block on the left. And also, each of these blocks is still being in motion. So give each of those blocks some kinetic energy. So it's 1, 2, 3 blocks for kinetic energy. Okay. I can be squared. So start there. All right, then. Yeah, let's do simple machines. All right, so pulley example of a simple machine. I have one over there. You guys see in class that flow system. If you get to see that up close, that gives you what's called a 7-to-1 mechanical advantage. So you're 7 times as strong. Okay? So you can lift something really heavy with a really tiny input force. That's kind of what you see right here. So what if you have a big old weight right here? What if this weighs like 30 newtons? But the spring scale over here might only read like 10 newtons. So you only need to pull at 10 newtons to lift it. Right? So you've amplified your strength by a factor of 3. That's what makes this like a 3-to-1 mechanical advantage. Okay? Now, how does that work? Right? And you can show this working with conservation of energy. I'll have you guys bring up some pulley systems. This is going to be another. Actually, I got your labs printed out right here. Right? So I referenced this one earlier. This somebody's going to get this paper in their hands. And then on the other side, I'll have you guys also do this lab. I'll have you guys bring up a bunch of different pulley systems. My poster, we're just focused on this one right here, the 3-to-1. So what's going on with this one? Right, so you see I wind the string around in such a way that it's sort of like this movable pulley here has like 3 strings pulling up on it. You see that? Right? So whatever this weight is, if this is a 30 Newton weight, you see it's been split 3 ways and the tension of the string is only a third of that, or 10 Newtons. Right? And that transfers over here, so you only have to pull at 10 Newtons. Right? Now, where's conservation of energy come in? Because you can't actually create energy. So even though you can amplify your strength in terms of force, you can't actually amplify the amount of energy that's going around. Right? It would be nice if you could, that you could run the entire world's energy supply on one lump of coal, but it doesn't really work that way, right? Right. So Oh, the catch is so what is work? Work is force times distance. So even if you have a small input force to lift a very large output force, large output weight, the catch is you have to pull lots and lots and lots of string. So guys, what if I pull like 30 centimeters? 30 centimeters. Guess how far this moves up? What's 30 divided by 3? 10 centimeters. Okay. So this weighs 30 newtons. It only moves up 10 centimeters. On the opposite end, I'm pulling with only 10 newtons, but I have to pull 30 centimeters, right? 30 times 10 equals 10 times 30. You guys get that? Right? That's what this is right here. So work input equals work output. Now that's a best case scenario. That's if it's 100% efficient. Okay. Which kind of leads to these two ideas down here. There's different names for mechanical advantage. It's ideal mechanical advantage versus actual mechanical advantage. Okay. Now, ideal is just based on the geometry, which is exactly what you're looking at. If you have 100% efficiency, like no frictional losses, nothing like that, it should be a 3-to-1 mechanical advantage. Okay. These distance ratios should be 3-to-1, and you amplify your strength by a factor of 3. But in the real world, I think there's maybe a little bit of friction, and maybe these strings aren't exactly vertical, and so there's a little bit of trigonometry. Yeah, okay, so in the real world, if you just take the actual ratio of the forces, it's probably a little bit less than 3-to-1. Maybe it's like 2.5-to-1 or 2.9-to-1, something like that. Okay, so it's called actual mechanical advantage. Okay. Now, there's different ways to get mechanical advantages. Here's your lab page. You could use a wheel. Guys, what if you have a string wrapped around the small diameter wheel versus you're pulling on the side of the large diameter wheel? You guys see it's get sort of like a seesaw leverage? You guys see that? Yeah. You can also amplify your strength this way, but again, the amount of energy doesn't actually change. So work input equals work output. You could, how about an inclined plane? You guys ever got a heavy box, maybe put on little wheels and it's really hard to lift, but you can push up an incline? Okay. So it turns out this H divided, or I should say the other way around, this L divided by this H represents your ideal mechanical advantage that way. If it's like a 3-to-1 ratio. Okay. Yeah. Here's a whole list of simple machines. Yeah, so got pulley, got a lever, we got wheel and axle, or so on. All these could represent simple machines to get some kind of mechanical advantage. Okay. Now here's the lever example. Okay. I don't know if I'll have you guys do this as a lab, but do you guys see that you could lift something very heavy with a small input force? Okay. But you do have to push down a long distance on this side of the lever to lift this up a little bit on this side. So force times distance still equalizes. Okay. Energy input equals energy output. Okay. And okay. Well, right. Here's switch these. Right. Here's efficiency for say like simple machines. Right. Okay. Okay. You know what? Okay. I do want to do this one with you guys, but I got 1 minute left, so I'm gonna pay that one for tomorrow. Okay. Here's the last thing I'll show you today. Okay. Remember I told you guys I'll show you how universal gravitation does simplify to MGH. Okay. So what if you had a tower that was fairly tall? So this radius 2 is a little bit different than this radius 1. Right? You're going from top down to Earth to sea level, right? Okay. So what you could do is you could set the difference in these universal gravity forms for this R2 and this R1 a little bit different. Okay. Then you can get a common denominator, which we did here. So I just go through a series of algebra steps. You can factor out this. And but then at the end of the day, you say, well, go even from the top of Mount Everest down to sea level. In terms of the radius of the Earth, that's very, very tiny change. So this R2 and R1 are almost the same. I call it basically R squared. Okay. And then, oh, look at this brown bit right here. It says GM over R squared, which represents a gravity field. And this difference in R represents the height change. And the mass is still this mass. Yeah. So that's how this simplifies to MGH, okay, which is what you use most time anyway. Okay. And then I'll have to save this next one for tomorrow also. Is you can also use this to derive escape speed. All right, but we are out of time today. So yeah, stop right there. All right, you guys have a good day and more energy tomorrow.